concept of air defense in 1940 was a desperate gamble disguised as military science. On paper, the mathematics of shooting down an airplane were understood, but in the chaos of combat, the equation was nearly impossible to solve. A standard anti-aircraft shell was a dumb instrument of brute force. It did not know where the enemy was. It only knew when its internal clock ran out. If a gunner estimated the range at 4,000 yards and set the timer for 5 seconds, the shell detonated at exactly that moment, regardless of whether the enemy bomber had turned, dived, or was even there at all. In the early days of the Second World War, the sky was vast, the planes were fast, and the shells were blind. In this war, battles were decided not just by the courage of the men in the trenches, but by the efficiency of the machines they operated. The harsh reality was that for every single aircraft brought down by ground fire, thousands of rounds were wasted, turning the sky black with smoke while the bombers flew on, untouched. At the War Perspective, we believe the best way to honor the past is to never let it be forgotten. If you believe in that mission, hit the subscribe button and join us on this journey. Now let us return to the gun decks and the desperate struggle against the rising power of aviation. To understand the magnitude of the problem facing the Allied forces, one had to stand on the deck of a battleship or in the muddy battery pits of London during the Blitz. The primary weapon against high-altitude bombers was the heavy anti-aircraft gun, such as the American 5-inch or the British 3.7-inch. These were powerful weapons capable of hurling a 50-pound explosive projectile miles into the atmosphere. However, the mechanism that triggered the explosion was a relic of a slower era. It was a mechanical time fuse, essentially a sophisticated pocket watch built into the nose of the shell. The process of firing a single effective shot was an agonizingly complex ballet of error. First, the rangefinder had to track the enemy aircraft, determining its distance, altitude, and speed. This data flowed into a mechanical analog computer, a director, which calculated where the gun should point, and crucially, how long the shell needed to fly before detonating. This time of flight was transmitted to the gun crew. A soldier inserted the shell into a fuse setter, a machine that physically rotated a ring on the nose of the projectile to set the timer. Only then was the shell loaded into the breech and fired. From the moment the range was measured to the moment the shell burst, 10 to 20 seconds might have elapsed. In those seconds, a Mitsubishi Zero or a Messerschmitt 109 could change course, dive, or climb. The shell would arrive at the predicted point in space, detonate exactly as ordered, and find nothing but empty air. The shock wave and shrapnel from a heavy AA shell were lethal, but only within a radius of roughly 50 to 70 feet. In the vast three-dimensional theater of the sky, missing by 100 feet was as good as missing by a mile. The statistics of this inefficiency were staggering. During the London Blitz, British gunners fired tens of thousands of rounds for every Luftwaffe bomber they destroyed. The ground was littered with shrapnel, barrels were worn smooth from continuous firing, and ammunition stockpiles were depleted at an alarming rate, yet the bombs kept falling. The logistical strain was immense. The convoys crossing the Atlantic had to carry millions of tons of explosive shells just to maintain a defense that was statistically unlikely to succeed. The situation was even more dire for the United States Navy in the Pacific. Their challenge was not just high-altitude level bombers, which flew in predictable straight lines, but dive bombers. Aircraft like the Aichi D-3A Val plummeted from the sky at steep angles, their speed and bearing changing rapidly every second. Mechanical directors could not keep up with the angular velocity of a plane diving directly at the ship. The gunners were forced to rely on barrage fire, simply filling a box of sky with as many explosions as possible and hoping the enemy pilot would be unlucky enough to fly through it. It was a strategy of saturation, not precision. Commanders watched in frustration as enemy planes wove through the black puffs of flak, dropped their torpedoes or bombs, and pulled away. The prevailing sentiment among the crews was one of helplessness. They possessed the firepower to obliterate anything that flew, but they lacked the means to deliver that power to the right coordinate at the right millisecond. The limitations of the mechanical time fuse created a psychological burden on the defenders. They knew that unless they achieved a direct hit, which required the shell to physically collide with the aircraft, a probability akin to shooting a bullet with another bullet, or a perfect time burst, their efforts were largely visual deterrents. The enemy pilots knew it too. They learned that if they jinked their aircraft or changed altitude slightly, the calculated bursts would explode harmlessly behind them. There was a third option, the contact fuse, which detonated only upon impact. But against a frail aircraft frame in a massive sky, relying on impact was a fool's errand. What the Allies needed was a weapon that bridged the gap. They needed a shell that did not rely on a gunner's estimation or a mechanical clock. They needed a projectile that possessed a degree of intelligence, a device that could sense when it was close enough to kill and decide on its own to detonate. This concept was not new. Inventors and science fiction writers had dreamed of influence fuses for decades. Patents existed for acoustic fuses that listen for engines, or magnetic fuses that sense the steel of a hull. But dreaming of such a device was easy. Building one that could fit inside a 5-inch shell was considered a physical impossibility. The device would have to be small enough to fit in the palm of a hand, yet complex enough to emit a signal, receive a reflection, and trigger a switch. More daunting than the miniaturization was the violence of the environment. When a 5-inch gun fired, the shell experienced an acceleration of 20,000 times the force of gravity. It spun at hundreds of revolutions per second. The force was enough to flatten a solid block of lead. To place delicate electronics, vacuum tubes, and glass components inside such a maelstrom and expect them to function was dismissed by most military ordnance experts as a fantasy. Yet as the war clouds darkened and the reports from the Battle of Britain highlighted the futility of current anti-aircraft measures, a small group of scientists in America began to look at the problem not as a fantasy, but as a necessity. The survival of the fleet in the cities of Europe depended on solving the gunner's nightmare. The era of guessing was over. The era of the smart weapon had to begin, regardless of the impossible physics standing in the way. In the summer of 1940, while the British struggled against the Luftwaffe, a quiet revolution began in Washington, D.C. It started not in a general's war room or a battleship's bridge, but in the academic halls of the Carnegie Institution. Vannevar Bush, the scientific advisor to the president, recognized that modern warfare had outpaced the military's traditional methods of invention. He established the National Defense Research Committee to harness the intellectual capital of American universities for the war effort. Within this sprawling organization lay a division known simply as Section T. The T stood for Tuve. Dr. Merle Tuve was a physicist of immense energy and pragmatic brilliance. He was not a man interested in theoretical perfection or academic accolades. He was interested in survival. While other scientists debated the nuances of atomic theory, Tuve looked at the reports coming from London and realized the immediate threat was the airplane. He understood that if the United States entered the war, its fleet and its cities would be vulnerable to the same terror that was currently leveling British neighborhoods. Tuve took command of Section T with a singular, driving philosophy that permeated every corner of his laboratory. He told his team that he did not want the best weapon in the world in 1945. He wanted a workable weapon in 1941. He famously declared, I don't want to be the son of a bitch who says, "I told you so," when the bombs start falling here. This sense of awful urgency defined the culture of Section T. It was a place where the deliberate pace of the scientific method was replaced by a frantic, industrial sprint. The objective was clear, but the path to achieving it was shrouded in technical darkness. Tuve and his team scrutinized every possible method for creating an influence fuse. They considered acoustic sensors that would trigger when they heard the roar of an aircraft engine. They looked at photoelectric cells that would detonate when the shadow of a wing blocked the sun. They investigated ground-controlled radio pulses, but one by one these methods were discarded. Acoustics were too slow. Sound moved at a crawl compared to the closing speed of a dive bomber. Photoelectrics were useless at night or in clouds. The team settled on radio reflection. The concept relied on the Doppler effect and radio interference, principles well understood in physics labs but never applied to ballistics. The idea was to turn the artillery shell into a miniature radio station. The shell would emit a continuous radio wave as it flew. When these waves struck a target, like the metal fuselage of a Japanese Zero, they would bounce back to the shell. As the shell approached the target, the reflected wave would return at a slightly different frequency than the transmitted wave, compressed by the speed of the shell. These two frequencies, the outgoing and the incoming, would mix inside the shell's electronics. As the distance closed, the interaction between the frequencies would create a beat signal. When this signal reached a specific intensity, indicating the shell was within 70 feet of the object, it would trip an electronic switch, detonating the explosive charge. It was a brilliant theoretical solution that solved the geometry of the gunner's nightmare. The shell did not need to hit the target, it only needed to pass nearby. It created a lethal sphere of destruction rather than a single point of impact. However, moving this idea from a chalkboard equation to a physical reality required overcoming a barrier that most experts deemed insurmountable. In 1940, radio technology was bulky, fragile, and hot. A standard radio set was the size of a piece of furniture filled with glass vacuum tubes, heavy transformers, and delicate soldered wires. Tuve proposed shrinking this entire apparatus down to the size of a milk bottle. Furthermore, this miniaturized radio station had to be self-powered. It could not rely on external batteries that would degrade in storage. It needed a power source that was inert until the moment of firing, then instantly sprang to life to provide the voltage necessary for the tubes to transmit. The skepticism from the military establishment was palpable. The Navy Bureau of Ordnance, steeped in decades of tradition, viewed the scientists of Section T with a mix of hope and suspicion. They knew the violence of a gun barrel better than anyone. They explained to Tuve that a 5-inch shell accelerated from 0 to 2,600 feet per second in a span of milliseconds. The rotational force was so extreme that it could rip internal components apart. To expect a glass vacuum tube, a device that would break if dropped on a hardwood floor, to survive such a cataclysm was, in their view, a waste of resources. Tuve ignored the pessimism. He gathered a motley crew of astronomers, cosmic ray researchers, and amateur radio enthusiasts. These were men used to building their own equipment, men who knew how to improvise. They set up shop in a garage in Maryland and later in the Department of Terrestrial Magnetism. The atmosphere was less like a military base and more like a high-stakes startup. There were no uniforms, only rolled-up sleeves and cigarette smoke. The initial experiments were crude. To test the ruggedness of components, they didn't have sophisticated centrifuges, so they improvised. They mounted radio tubes inside metal casings and dropped them from the roof of the laboratory onto the concrete driveway below. They fired components out of smoothbore guns into lead blocks to see what survived. Most of the time, the result was a pile of shattered glass and twisted wire. The early prototypes failed continuously. Tubes imploded, filaments snapped, and batteries leaked. But with every shattered tube, the team learned something. They analyzed the failure points, the stress fractures, and the weaknesses of commercial electronics. Tuve drove them relentlessly. There were no weekends off. The war in Europe was going badly, and the Atlantic was becoming a graveyard for Allied shipping. The scientists knew that every day they spent debugging a circuit was a day the fleet remained vulnerable. They were attempting to compress 20 years of electronic evolution into a matter of months. The core of the problem remained the vacuum tube. It was the heart of the system, the component that generated and processed the radio waves. If they could not make glass as strong as steel, the project was dead. The physics of the gun barrel were non-negotiable. The electronics had to adapt to the gun, not the other way around. And so the focus of Section T narrowed to a single fragile challenge: how to keep a glass bulb intact while being kicked by a giant. The obstacle standing between the Allied forces and a revolution in air defense was a piece of glass no larger than a pinky finger. The vacuum tube was the transistor of the 1940s, the essential valve that controlled the flow of electricity to generate radio waves. But unlike the solid-state transistors that would follow decades later, vacuum tubes were mechanical structures. Inside the glass envelope, a delicate filament, a grid of fine wire, and a metal plate were suspended in a vacuum. Under normal conditions, these internal parts were stable, but inside a gun barrel subjected to 20,000 Gs of force, the internal structure would collapse. The filament would snap like a dry twig. The grid would distort and short out against the plate. Section T knew they couldn't rewrite the laws of physics, so they had to rewrite the manufacturing process of the vacuum tube. They turned to the companies that built hearing aids, Raytheon and Sylvania. These firms were already accustomed to making smaller, somewhat more durable tubes for portable devices. But durable for a hearing aid meant surviving a drop from a shirt pocket, not being fired from a cannon. The engineers began a rigorous, destructive process of trial and error. They took standard hearing aid tubes and potted them in wax, hoping the buffer would absorb the shock. It helped, but not enough. The internal supports were still too weak. They realized they had to redesign the architecture of the tube itself. The breakthrough came from analyzing exactly how the tubes failed. They discovered that the long, thin glass stems that held the internal wires were snapping under the rotational torque of the spinning shell. The solution was to shorten everything. They reduced the size of the glass envelope and thickened the glass walls. They redesigned the internal mounts, anchoring the filament and grid at both ends, rather than leaving them cantilevered like diving boards. But the most critical innovation was the potting material. The team experimented with dozens of substances to fill the empty space inside the projectile's nose cone, encasing the delicate electronics in a solid block. They needed a material that would flow like liquid when poured, but harden into a rigid, supportive mass that wouldn't crack under pressure. They eventually settled on a special wax compound that locked every component in place. When the shell fired, the electronic assembly moved as a single, solid unit. The glass tubes couldn't vibrate. The wires couldn't whip around. They were frozen in a matrix of wax. Testing this ruggedness required more than just dropping tubes off the roof. The team utilized a specialized smoothbore gun at the Naval Proving Ground in Dahlgren, Virginia. They would build a prototype fuse, load it into a slug, and fire it straight up. Since the shell was designed to self-destruct, they couldn't just inspect the wreckage. They needed to know if the radio was working during the flight. They set up listening stations on the ground, tuning receivers to the frequency of the fuse. When the gun fired, the engineers held their breath, watching the oscilloscope screens. For months, they saw nothing but static, the silence of a broken device. But gradually, the blips began to appear. A fuse would scream out of the barrel, and the radio signal would sing clear and true for the entire flight. It was the sound of success. While the tubes were the primary hurdle, the power source was a close second. A standard dry cell battery had a shelf life of only a few months. In the humidity of the Pacific, a battery might be dead before the shell was ever loaded into a gun. A fuse that didn't power up was a dud, and a dud was a death sentence for the sailors depending on it. The solution was a stroke of genius known as the reserve battery. Instead of storing energy chemically like a standard battery, the reserve battery was a mechanical device. It consisted of plates of zinc and carbon, but the electrolyte, the liquid acid needed to create the reaction, was stored separately in a small glass ampule. As long as the glass remained intact, the battery was inert. It could sit on a shelf for 10 years and never lose a volt. The activation mechanism used the violence of the launch itself. When the gun fired, the setback force, the immense kick of acceleration, shattered the glass ampule. The centrifugal force of the spinning shell then forced the liquid electrolyte outward, flooding the plates. Within a tenth of a second, the battery went from 0 voltage to full power, waking up the radio transmitter just as the shell left the muzzle. It was a battery that only existed when it was needed, born in the fire of the gun barrel. This combination of the ruggedized vacuum tube and the setback battery created a device that was paradoxically delicate and indestructible. It was a sophisticated radio set that could be used as a hammer. However, proving it worked in a vertical test shot was one thing. Proving it could detect a target was another. The team moved to test firings against drone targets, canvas sleeves towed behind aircraft or simple wooden gliders. The results were immediate and terrifyingly effective. In one early test, a proximity fuse shell detonated so close to the drone that it shredded the target completely. The observers on the ground, accustomed to seeing hundreds of shells miss, were stunned. They weren't watching a lucky shot. They were watching a system that refused to miss. But as the design solidified, a new massive problem emerged. Making 10 prototypes in a laboratory was an artisan process. Making 10 million of them for the war effort was an industrial nightmare. The fuse required tolerances closer than a Swiss watch, but it had to be built by the millions, quickly, by a workforce that had never seen such technology. The challenge shifted from the laboratory bench to the assembly line. The impossible idea was now real. Now it had to be mass-produced in total secrecy, right under the nose of a nation at war. The transition from a laboratory prototype to a mass-produced weapon of war is often where great inventions die. For the VT Fuze, officially designated the variable time fuse to confuse enemy intelligence, the manufacturing challenge was staggering. The United States needed millions of these units, and they needed them yesterday. But this was not like stamping out sheet metal for Jeeps or casting iron for tank treads. This was the mass production of precision electronics, a field that barely existed on an industrial scale. The War Department faced a dilemma. They could not simply hand the blueprints to a single company. No single manufacturer had the capacity or the diverse expertise required. The fuse was a hybrid of chemistry, the battery, glass blowing, the tubes, and precision assembly. Instead, the government orchestrated a massive decentralized manufacturing network that spanned the entire American industrial landscape. Major corporations like Crossley, RCA, Eastman Kodak, and McQuay Norris were drafted into the effort. These were companies known for making radios, cameras, and piston rings, not munitions. They had to retool their factories almost overnight. But the real challenge lay in the secrecy. The VT Fuze was classified top secret, a level of security shared only with the Manhattan Project. The fear was that if the Germans or Japanese recovered a dud shell, they could reverse engineer the technology and use it against Allied bombers, or worse, develop electronic countermeasures to jam the fuses. To maintain this secrecy, the manufacturing process was compartmentalized. A worker on the assembly line at Crossley might be soldering a specific circuit board, but she had no idea what it was for. She might be told it was a component for a new type of radio or an engine part. The final assembly was done in secure facilities where the pieces came together, often under armed guard. The scale of the mobilization was immense. At the peak of production, over 80,000 Americans were working on the VT Fuze project. Most of them were women. They sat at long workbenches in converted factories, peering through magnifying glasses, their fingers manipulating tweezers and soldering irons with surgical precision. They were building the most advanced electronic device of the era, yet they were forbidden from speaking about their work even to their families. Quality control became an obsession. In a standard radio, if a tube was slightly off spec, the user might hear a bit of static. In a VT Fuze, a defect meant the shell might explode in the barrel of the gun, killing the entire gun crew. This was not a theoretical risk. Early premature detonations and testing had heightened the anxiety of everyone involved. To ensure reliability, the factories implemented testing standards that were unheard of in civilian industry. Every batch of tubes was subjected to centrifuge tests. Every battery was checked. Samples from every production run were taken to proving grounds and fired. If a sample lot showed a failure rate above a tiny fraction, the entire run, thousands of units, was scrapped. It was a ruthless, wasteful, and necessary process. One of the most remarkable aspects of this industrial feat was the rapid evolution of the product on the line. Section T didn't stop innovating just because production had started. They constantly fed improvements back to the factories. When they found that humidity was affecting the circuits, they developed better waterproofing. When they found a way to make the tube smaller, they reconfigured the assembly. The factories had to be agile, changing their tooling and procedures on the fly while maintaining a frantic pace of output. The supply chain was a logistical ballet. Glass for the tubes came from one supplier, the special wax for potting from another, the zinc plates for the batteries from a third. All these streams of material had to converge at the assembly plants perfectly. A shortage of a single tiny resistor could halt the entire line. The Army and Navy assigned expediters to the project, men whose sole job was to smash through bureaucratic bottlenecks and ensure that Section T got whatever it needed, whenever it needed it. By 1942, the flow of fuse began to turn into a river. The factories were churning out thousands of units per day. These were packed into nondescript wooden crates, marked with misleading codes, and shipped to naval ammunition depots. There, they were screwed into the noses of 5-inch shells. The fuses looked unremarkable from the outside, just a plastic nose cone instead of the usual metal tip. But inside, they held the power to change the geometry of war. The security was so tight that even the captains of the ships receiving the new ammunition were kept in the dark about its true nature. They were given sealed orders. Do not load these shells until combat is imminent. Do not fire over friendly territory. The implications were clear. This weapon was precious and it was dangerous. As the crates accumulated in the magazines of the Pacific Fleet, a tension built among the few who knew the secret. They had built the impossible machine. They had ruggedized the vacuum tube, invented the liquid battery, and mobilized an army of workers to build it. But the ultimate test could not be simulated in a lab or a proving ground. The true test would come when a young sailor, terrified and exhausted, loaded one of these shells into a gun and fired it at a Japanese plane diving for his ship. The silent factory lines had done their job. The women with the soldering irons had built the hardware. Now it was up to the Navy to prove that American industry had indeed created a miracle. The fuses were on their way to the war, traveling across the ocean in the dark holds of supply ships, waiting for the moment to wake up. By late 1942, the South Pacific had become a graveyard of ships. The waters around Guadalcanal were known as Iron Bottom Sound for the sheer tonnage of steel resting on the ocean floor. It was here, in this theater of attrition and exhaustion, that the crate-laden supply ships finally arrived. They carried the secret fruit of the American industrial mobilization, the Mark 32 shells. These were the first combat-ready projectiles equipped with the VT Fuze. The distribution of these shells was handled with a level of paranoia usually reserved for diplomatic cables. They were not issued to every ship, nor were they piled high in every magazine. Initially, they were entrusted to a select few vessels, the modern light cruisers that acted as the anti-aircraft umbrellas for the fleet. One of these ships was the U.S. Helena. The Helena was a Brooklyn-class light cruiser, a floating fortress of rapid-fire 6-inch and 5-inch guns. Her crew was battle-hardened, having survived the attack on Pearl Harbor and the brutal night engagements of the Solomons. They knew the terrifying routine of air defense intimately, the scream of the klaxon, the rush to battle stations, and the frantic cranking of the fuse setters as they tried to guess the range of incoming Japanese aircraft. When the new shells were brought aboard, the gunners' mates noticed the difference immediately. The nose cones were not the usual metallic tips. They were made of a strange, translucent plastic. And most confusing of all, there were no timing rings to set. The order came down from the bridge. Load and fire. Do not set fuses. To a veteran gunner, this instruction sounded like madness. Firing a shell without setting a time fuse usually meant it would act as a dumb projectile, detonating only on impact or at the extreme end of its flight. But the orders were absolute. On January 5, 1943, the Helena was patrolling off the coast of Guadalcanal, screening a convoy of transports. The radar operators picked up a formation of Japanese Aichi D-3A VAL dive bombers. These were the same nimble, fixed-gear aircraft that had devastated the Pacific Fleet at Pearl Harbor. They were dangerous, precise, and flown by pilots who knew how to exploit the blind spots of American gunnery. As the VALs tipped over into their dives, plummeting toward the task force, the Helena's 5-inch guns swiveled to track them. In a traditional engagement, the fire control computer would have been screaming out time-of-flight data, and the loader would have been frantically adjusting the nose of every shell. But on this day, the loaders simply shoved the Mark 32 rounds into the hoist. The guns roared. Inside the barrel of the first shell, the glass ampule of the battery shattered. The centrifugal force spun the electrolyte into the plates, and the vacuum tubes, encased in their wax tomb, glowed to life. The radio transmitter began pulsing a signal at the speed of light. The Japanese pilot of the lead bomber likely never saw the shell. He was focused on his dive angle, lining up his sights on the transport ship below. He expected the usual flak pattern, black puffs of smoke exploding hundreds of feet behind him or below him, the result of gunners guessing his altitude and getting it wrong. He did not know that a sentient machine was hurtling toward him. The shell passed within 70 feet of the valve. The radio waves bounced off the aluminum skin of the bomber and returned to the receiver in the shell's nose. The frequency shift triggered the firing circuit. There was no hesitation, no mechanical delay. The shell detonated instantly. From the deck of the Helena, the crew witnessed something defying their experience. Usually it took hundreds of rounds to bracket a diving plane, filling the sky with shrapnel in the hopes of a lucky hit. This time, the lead plane simply disintegrated. A second salvo was fired at a second attacker. It too blossomed into a fireball. The Helena had swatted the enemy from the sky with a precision that looked less like gunnery and more like magic. The report that went back to Washington was understated but momentous. It noted that the Helena had engaged the enemy with the new ammunition and achieved a 50% kill ratio on the first pass, a statistic that was mathematically absurd compared to the 0.1% kill ratio of standard time fuses. The news spread quietly through the upper echelons of the Navy. The funny fuses worked, but with success came a renewed wave of anxiety. The effectiveness of the weapon confirmed the worst fear of the War Department. If the Japanese recovered a dud, they would see that the Americans had miniaturized radar and put it inside a bullet. If they reverse-engineered it, the B-29s bombing Japan would be slaughtered. If they found a way to jam the frequency, the advantage would be lost. Strict rules of engagement were imposed. The VT Fuze could only be used over open water, where a dud round would sink safely to the bottom of the ocean. It was forbidden to fire them over land or near islands where wreckage could be recovered. This restriction frustrated the Army, whose troops were being pounded by the Luftwaffe in Europe. But the Navy held the line. The secret of the fuse was too valuable to risk for a tactical gain on the ground. It was a strategic asset for the control of the sea. As 1943 progressed, the miracle shell began to change the psychology of the Pacific War. The Japanese pilots, who had once flown with a degree of arrogance against naval gunfire, found the air around American ships becoming impossibly lethal. The wall of steel was no longer just a metaphor, it was a sensory reality. The probability curves had shifted. An American task force was no longer a target, it was a death trap. The success on the Helena vindicated the wild-eyed scientists of Section T. It proved that the wax-potted tubes could survive the cannon's kick. It proved that the battery would wake up in time, but mostly it proved that the era of the dumb projectile was over. The United States had introduced the first smart weapon to the battlefield, and for the pilots of the Imperial Japanese Navy, the sky had suddenly become a very small, very dangerous place. For 2 years, the VT Fuze remained a creature of the sea, guarded by the Navy's strict overwater-only mandate. The fear of technology transfer paralyzed its deployment on land. The War Department was terrified that a single unexploded shell, recovered from a muddy field in France or Italy, would be shipped to a Berlin laboratory, revealing the secret of the vacuum tubes to German scientists. And so, while American destroyers in the Pacific enjoyed near immunity from air attack, the infantry and artillery in Europe fought the old-fashioned way. But by late 1944, the calculus of risk changed. The Allies had landed at Normandy and were pushing toward the German border. The Luftwaffe, though diminished, was still a threat, but a new terror had emerged, the V-1 flying bomb. These buzz bombs, rudimentary cruise missiles, were raining down on London and the vital port of Antwerp. They were fast, small, and flew in straight lines, perfect targets for the VT Fuze, provided the guns could be placed on land to intercept them. General Eisenhower and the combined chiefs of staff weighed the options. The war was entering its final, desperate phase. The secret of the fuse was still paramount, but the cost of withholding it was measured in American lives, in strategic delays. Then came the intelligence reports of a massive German buildup in the Ardennes forest. The enemy was preparing a last-ditch counteroffensive, a winter surge designed to split the Allied armies and recapture Antwerp. This was the Battle of the Bulge. The Germans attacked in December 1944 under the cover of thick cloud and fog that grounded the Allied air superiority. Without air support, the American troops were vulnerable. They faced waves of German infantry and armor pushing through the snowy forests. The situation was critical. The lines were bending, threatening to break. In a decision that historian James Finney Baxter III would later call a calculated risk of the highest order, the ban was lifted. Eisenhower authorized the release of the VT Fuze for unrestricted use by land artillery. The secret was out of the bag. Now it had to pay for itself in blood. The effect was cataclysmic. Until this moment, artillery fighting against infantry relied on time-on-target bursts or impact fuses. An impact fuse hit the ground and exploded, sending shrapnel upward and outward. If the soldiers were in foxholes or trenches, the earth absorbed most of the blast. A time fuse could be set to burst in the air, raining shrapnel down into the trenches, but getting the timing right required precise estimation of range and height. If the timing was off by a fraction of a second, the shell buried itself harmlessly or burst too high to be effective. The VT Fuze changed the geometry of the battlefield. When fired against ground targets, the radio sensor didn't look for a plane, it looked for the ground. As the shell arched over the German positions, it sensed the earth approaching. When it reached the optimal height, roughly 20 to 50 feet above the terrain, it detonated. This created what artillerymen called an airburst. The shell exploded directly overhead, driving shrapnel straight down into the foxholes, the open turrets of half-tracks, and the dense pine forests. There was no cover. The trees themselves became force multipliers, shattering into lethal splinters under the downward blast. For the German soldiers in the Ardennes, the experience was terrifying. They were veterans. They knew the rhythm of artillery. They knew that if they dug deep enough, they could survive a barrage. But suddenly the shells were exploding with impossible consistency exactly above their heads. They reported that the Americans had developed a new, demonic accuracy. The psychological impact was as devastating as the physical one. It seemed there was no place to hide. General George Patton, whose Third Army was racing to relieve the besieged town of Bastogne, wrote to the War Department with characteristic bluntness, "The new shell with the funny fuse is devastating. The other fellow thinks it is sporting to shoot at him, but when he shoots at you and you have this thing, it is murder." He credited the fuse with breaking the back of the German infantry assaults. In the skies over Antwerp, the fuses were equally decisive against the V1s. Anti-aircraft batteries, now equipped with the VT shells and coupled with new radar-guided directors, formed a nearly impenetrable belt of defense. The success rate of shooting down the buzz bombs jumped from roughly 20% to nearly 80% in a matter of weeks. The diver belt, as the defensive line was called, saved the port of Antwerp, ensuring the supply lines for the final push into Germany remained open. The gamble had paid off. The Germans, reeling from the onslaught on two fronts, never had the chance to recover a dud and analyze it. By the time they might have found one in the snow of the Ardennes, their industrial capacity to replicate it was being pulverized, and their armies were in retreat. The secret weapon had been unleashed at the precise moment it could tip the scales of the entire European theater. The funny fuse had evolved from a naval defensive tool into a supreme offensive weapon. It demonstrated a terrifying versatility. In the Pacific, it protected the ships. In Europe, it shattered the armies. The technology of Section T, born in a garage and built by women in secret factories, had arrived in the frozen forests of Belgium to deliver the final verdict of the war. While the artillerymen in the Ardennes marveled at their new power to burst shells over foxholes, the sailors in the Pacific were facing a horror that defied all military logic. By late 1944, the Imperial Japanese Navy had ceased to function as a traditional fleet. They had lost their carriers, their best pilots, and their fuel reserves. Faced with the relentless advance of the American Armada toward the home islands, Japan turned to a tactic of pure spiritual desperation, the Kamikaze. The Divine Wind was not merely a suicide attack. It was the conversion of human beings into intelligent guidance systems for anti-ship missiles. A conventional bomber dropped its payload and tried to escape, meaning it was vulnerable for only a few moments. A kamikaze, however, was locked on a one-way vector. The pilot did not break off. He flew through the flak, ignoring damage, intent on slamming his explosive-laden aircraft directly into the flight decks and superstructures of American carriers. For the gun crews on the U.S. ships, the psychological strain was immense. They watched as planes burned, lost wings, and smoked, yet kept coming. A damaged kamikaze was just as lethal as an intact one. To stop a suicide plane, it was not enough to damage it or kill the pilot. The aircraft itself had to be structurally disintegrated in midair. It had to be turned into debris before it crossed the gunnel. This was the ultimate test for the VT Fuze. The standard 5-inch shell with a mechanical time fuse was simply too slow to react to the erratic, terrified maneuvering of a pilot plunging toward his death. The time to kill had to be instantaneous. The Navy poured resources into upgrading the fleet, replacing the older Mark 32 shells with the improved Mark 53s, optimized for the violent, chaotic engagements of the final approach. The climax of this duel between the suicide pilot and the electronic shell occurred during the invasion of Okinawa in the spring of 1945. It was the Typhoon of Steel, the largest amphibious assault in the Pacific War. The Japanese High Command launched massive waves of kamikazes, hundreds of planes swarming the picket destroyers that stood guard around the fleet. These destroyers, small and unarmored, were the primary targets, the first line of defense that had to be smashed. On the radar screens in the combat information centers, the blips merged into solid blobs of light. The sky filled with aircraft, Zeros, Vals, Bettys, even primitive biplanes, all hurtling toward the ships. The response from the American fleet was a wall of fire so dense it seemed solid. The 5-inch guns, fed by continuous hoists of proximity-fused ammunition, fired as fast as the loaders could throw the shells into the breaches. There was no need to calculate the precise distance to each diving plane. The directors simply pointed the guns at the target's bearing, and the fuses did the rest. Observers described the scene as a meat grinder. As a Japanese formation approached, the leading edge of the American defensive fire would meet them. The VT fuses sensed the aluminum of the planes and detonated at the optimal lethal distance. The sky erupted in a continuous, rolling thunder of black smoke and orange flashes. Planes did not just crash, they dissolved. Wings were sheared off by the blast waves. Engines were pulverized by the high-velocity shrapnel. In one engagement, the destroyer USS Hadley faced a swarm of 10 kamikazes attacking simultaneously. In the past, this would have been a death sentence. But the Hadley's gunners firing VT rounds shot down every single attacker before they could strike. The ship was surrounded by a ring of splashing debris, the remnants of 10 aircraft destroyed by the invisible radio fingers of Section T's invention. The statistics from Okinawa painted a stark picture of technological dominance. In the early years of the war, it took an average of nearly 2,000 rounds of heavy anti-aircraft ammunition to shoot down a single plane. With the VT Fuze, that number dropped to less than 500. The efficiency of the defense had quadrupled. But even that statistic masked the true impact. Against a plane diving at 400 miles per hour, efficiency meant the difference between a near miss and a survival. The Japanese pilots, communicated with by radio until their final moments, reported a terrifying phenomenon. They claimed the American ships were surrounded by force fields. They could not get close enough to dive. The flak was not just intense, it was intelligent. It tracked them. It waited for them. This dominance allowed the U.S. Navy to operate directly off the enemy coast for months, sustaining a siege that would have been impossible with conventional ammunition. The picket ships took heavy damage, and many were lost to the sheer volume of attacks, but the fleet survived. The Kamikaze strategy, designed to bleed the American Navy white and force a negotiated peace, failed because the trade-off ratio was broken. The Americans could shoot down the planes faster than Japan could launch them. The sailors on the decks, sweeping the hot brass casings of thousands of spent shells into the ocean, understood what had saved them. They called the shells funny fuses or buckets of sunshine. They didn't know about the vacuum tubes or the glass ampules or the women in the factories in Ohio. They only knew that when they pulled the trigger, the enemy died. The VT Fuze had effectively nullified the last, most desperate tactical innovation of the Japanese Empire. It had turned the suicide attack from a guaranteed trade into a futile waste of life. The psychological blow to the Japanese command was severe. They had thrown their spirit and their bodies against the machine, and the machine had won. As the smoke cleared over Okinawa and the fleet turned its eyes toward the invasion of the main islands of Japan, the VT Fuze stood as the silent victor. It had paralyzed the pilots of the rising sun. It had proven that in the crucible of total war, courage alone could not overcome a weapon that could think. The gunner's nightmare of 1940 had been replaced by the pilot's nightmare of 1945. The skies belonged to the engineers. When the final surrender documents were signed on the deck of the USS Missouri in Tokyo Bay, the world's attention was fixed on a different scientific marvel. The atomic bombs dropped on Hiroshima and Nagasaki had ended the war with a blinding flash of cosmic violence. They were the visible, undeniable punctuation marks of the conflict. In the shadow of the mushroom cloud, the story of the funny fuse remained obscured by the very secrecy that had made it successful. Yet among the highest ranks of the military and scientific communities, there was a quiet consensus. The VT Fuze was the unsung equal of the Manhattan Project. The scale of the effort rivaled the building of the bomb. By the war's end, the United States had spent over $1 billion, an astronomical sum in the 1940s, on the development and production of the proximity fuse. The industrial mobilization had involved over 300 different companies and touched nearly every state in the Union. It was a triumph of logistics and manufacturing as much as it was a triumph of physics. The Americans had not just invented a gadget, they had created an entirely new industry from scratch, producing over 22 million fuses by VJ Day. Vannevar Bush, the architect of the American scientific war effort, later stated that the proximity fuse was one of the three most critical technologies of the war, standing alongside the atomic bomb and radar. He argued that while the bomb ended the war, the radar and the fuse won it. Without the fuse, the defense of London against the V-1s might have failed. Without the fuse, the Battle of the Bulge could have dragged on into a stalemate, bleeding the Allied armies dry. Without the fuse, the Pacific Fleet might have been crippled by the Kamikaze onslaught, delaying the advance on Japan by months or years. The legacy of Section T extended far beyond the capitulation of the Axis powers. The VT Fuze marked a fundamental shift in the nature of warfare. Before 1940, weapons were mechanical, relying on gears, springs, and chemical explosives. After 1945, weapons became electronic. The smart projectile, capable of sensing its environment and making a decision, was the ancestor of every guided missile, every smart bomb, and every automated defense system that would follow. The engineers who figured out how to pot vacuum tubes and wax had inadvertently laid the groundwork for the ruggedized electronics that would eventually take humanity to the moon. However, for the men who fought, the legacy was personal, not technological. It was measured in the ships that didn't sink and the friends who didn't die. Thousands of American sailors returned home because a small glass tube held together in the roar of a 5-inch gun. Infantrymen who survived the Ardennes owed their lives to a radio signal that cleared the way before them. The fuse had done exactly what Merle Tuve had demanded in those frantic early days. It had arrived in time to do the work. The scientists of Section T returned to their universities and laboratories, largely uncelebrated by the public. Tuve, true to his pragmatic nature, shunned the spotlight, believing that the work spoke for itself. The grand secret was slowly declassified, but it never captured the public imagination like the splitting of the atom. It was a weapon of defense, of efficiency, and of preservation, lacking the theatrical horror of the nuclear age. Yet the impossible idea stood as a testament to a specific moment in history where desperation met ingenuity. It proved that when faced with an existential threat, the barriers of impossible physics could be broken. The gunner's nightmare had been solved not by training better gunners, but by giving the shell itself a brain. The war had begun with biplanes and battleships, relics of the 19th century. It ended with jet engines, nuclear power, and electronic brains. The VT Fuze sat quietly at the center of this transformation, a small wax-filled nose cone that had paralyzed the pilots of the rising sun and broken the armies of the Third Reich. It was the silent sentinel of the Allied victory, the hidden ace in the sleeve of democracy. The VT Fuze was more than just a clever mechanism. It was the precise application of American intellect to the brute chaos of war. It bridged the gap between the erratic human hand and the unforgiving mathematical reality of the battlefield. By turning the artillery shell into a sentient predator, the engineers of Section T did not just improve a weapon, they redefined the philosophy of engagement. They proved that industrial might, when coupled with scientific daring, could create a wall of steel that no amount of fanatical courage could penetrate. The legacy of this innovation is written in the survival of the fleet and the liberation of Europe. It stands as a reminder that in the darkest hours, when the odds seem insurmountable, the fusion of science and resolve can turn the tide of history. These are the stories of the hidden gears that drove the machine of victory, and that is why these tales must be told.